Now we do more complex numbers problems and exercises. So first we want to compute 1 plus I to the power 24. Okay, so we're using the exponent. We can write this one as 1 plus I to the power 4 to the power 506. Okay, and after that we can use 1 plus I square to the power 506. Okay, first we compute 1 plus I squared. 1 plus I squared is using the regular algebra, or just the fact that we know that a plus ib squared is a squared minus b squared plus 2iab. We can use this fact here, given that a is equal to b is equal to 1 in this case. So we get 1 squared minus 1 squared plus 2i, because a times b is just 1. So we get 2i. Okay, now let's go back here and plug the value of 1 plus I squared. So we get 2I squared to the power 506. Okay, so we know that we can do this one as 2 to the power 2 to the power 506 times I squared to the power 506. Okay, we get 2 to the power 12 times I squared is minus 1, but since this one is an even number, we're gonna get 1. Okay, so I squared is minus 1 to the power of an even number, that's 1. So that means our value here is 1 plus I to the power 2024 is 2 to the power 1012. Okay, now we are asked to find what's the next. The next one is 1 plus 3i. Okay, so 1 plus 3i using the same technique as here. Okay, so a is 1 and b is 3. So here we have 1 squared minus 3 squared, which is 9, plus 2i ab is 3. Okay, times 3. So we get minus 8 plus 6i. Okay, 1 plus 3i squared is this one. Okay, now we compute 1 plus 1 minus 3i squared. We can use the similar result that we proved, which tells the fact that a minus ib squared is a squared minus b squared minus 2iab. Okay, so we proved it in one of the videos. Check it. So here we're going to use that. So here a is 1, b is minus 3 squared, which is 9. So 1 minus 9 minus a times b, 1 times minus 3. So we get minus 8 plus minus is a plus. So plus, I forgot the 2 here. So I need to add the 2. So minus times minus is a plus. So we get 6i. Okay, so 1 minus 3i is minus 8 plus 6i's. Okay, now we want to compute 1 minus 3i's times 1 plus 3i's. Okay, so we said that when we have a minus ib times a plus ib, we said we have a squared plus b squared. So in this case, a is 1 and b is 3 or minus 3, because we're going to square it. So here we have a squared, 1 squared, plus minus 3 or 3 squared. So we have 1 plus 3, which is 9. So we have 10. Okay. The next value that we're going to compute is 1 over 5 minus 9. Okay. So here we use the conjugate. So the conjugate of this number, remember that the conjugate of number z, a plus ib, the conjugate is a minus ip. So here we're gonna do 5 plus 9i over 5 minus 9i times 5 plus 9i. And we use the fact here that we know, the fact that we know here, this one, sorry, this one, okay, in the bottom. So in this case, we have just 5 squared plus 9 squared, and the top we have 5 plus 9i. So in the bottom we have 25 plus 81, which is 106. On the top we have 5 plus 9i. So let's write it in algebraic form. We have 5 over 1 over 6 plus 9 over 1 over 6i. Okay, so this is our value here. Okay, the next question that we are asked to do is, let me just get more space. The next question that we are asked is, in general, we want to compute z plus z bar and z minus z bar and see what we get. So let z equal a plus ib with ab in R, real numbers. Okay, so z bar in this case, it's a minus ib. So you want to compute the sum of these two numbers. So we said when we have two complex numbers, when we add them, we just add the real part with the real part and the imaginary part with the imaginary part without forgetting the I. So here we add a plus a, which is 2a, plus I. So the imaginary part here is b plus minus b. Plus minus b, which is 2a plus b plus minus b is 0. That means 0. So we have 2a. That means this one is real. Okay? So we have a number that's real. So we're gonna say a complex number is real if and only if the sum of, sorry, here z bar, sorry, that's a mistake, z bar. So the sum of the complex number and its conjugate is a real number. So if you have a number and its conjugate is a real, it's real, okay. Now let's, sorry, what did I want to say? I said let's compute z, and let's stabilize this one. So z plus z bar is 2a, and let's compute z minus z bar. That's the one that we need. Okay. Okay, so we have z minus z bar, it's a plus ib minus a plus ib, which is 2ib. Okay, so here z minus z bar, 2ib, and z plus z bar is 2a. So this is a number that's in C, and in fact it's a pure imaginary. We write it IC. This is the notation for imaginary, pure imaginary numbers. But this one is in R because A is real. Okay, okay, now we can prove that a number is real, a complex number is real if and only if the sum of the number with its conjugate is real. We can say that a number is a pure imaginary if the difference of the number and its conjugate is pure imaginary. So that's the result that we want to say. Okay, we will have to add more, but I think we had covered this one. We covered the conjugate. Okay, another thing that we need to note is when we have z bar, we have a squared plus b squared. Okay, so that's the models. Okay, given a number z, we have, and this is the complex plane, we have, let's say this is our z, it has a and b. So starting from the origin, this length here is called the modulus, and it's noted by this one, like the absolute value. So which is equal to the square root of a squared plus b squared. But we have seen here that this is square root of z times z bar. Okay, this is the definition of the modulus. Okay, let's say we have let's say z is 1 plus I. So what's the modulus of z? So it's a squared plus b squared, which is 1 plus 1, which is 2. So it's square root of 2. Okay, we can prove it. It's the square root of z times z bar. It's 1 plus I times 1 minus I. But remember what we said about the case here when we have a plus ib times a minus ib, which is equal to a squared plus b squared. And a squared is 1 and b squared is 1. So we have 1 squared plus 1 squared, which is 2. So the same thing. So the modulus, it's very important. We're going to use it later when we're dealing with more complex numbers. Thank you.